All right, so last time we were discussing quotient topology. Remember that if we have an onto map, so X topological space and P is onto, and we may define a topology on Y, the quotient topology. What's that? So a set in Y is called open if and only if P inverse of U is open in X. Okay. This is the weakest topology on Y, which makes the projection map onto. This is the weakest topology on Y, which makes P X to Y continuous. Okay, it is called the quotient topology. It is called a quotient, not the, but a quotient topology on of X star. Okay, we wrote the following proposition last time, but we didn't have time to prove it. So let's do that. Okay. So let be a quotient topology. And F be any map, where Z is not a set, but it's a topological space. It's a topological space. Then F is pardon. Burada Y'den tarif edilmiş. Ben geçen sefer ne yazdım? X'ten yazdım değil mi? Tamam. Then F induces a map. Onu neyle gösterdim? F bar'la mı gösterdim yoksa G falan mı? Tamam. F bar diyeyim. From Y. Ya bu da X. Neyse tamam. Y to Z. So that nedir? F eşittir P composition, önce P ile sonra F bar'la gideceğiz. If and only if and only if F is constant on each fiber of P. Fiber dediğimde şu, yani her bir noktanın ters görüntüsünde sabit olacak. For all y in y. Moreover, in this case, f bar is continuous if and only if f is continuous. Okay, now why is that? Şimdi elimizde ne var? So we have x here, and then we have projection onto y, and we have map f. I wonder if there is a map here, f bar, so that this diagram is commutative, okay? What we mean by commutative is this. F is equal to f bar composition P, okay? Is there such a map? Okay. Şöyle diyeyim, yani there exist. Ama var mı böyle bir map? Şimdi böyle bir map varsa, if such f bar exists, then of course, so diyelim ki x1, x2 are in P inverse of y for some y in y. If there is such f bar, then of course yani ne diyoruz? Şurada bir x1, x2 olsun. Öyle ki her ikisi de y noktasına gidiyorlar. Bu diyagram komutatifse x1 ile x2'nin görüntüsü y olduğuna göre y'nin görüntüsü burada tek bir eleman olacak. O zaman bu ikisi de f altında o elemana gitmek zorundalar. Dolayısıyla da f x1 ve x2'de aynı değeri almalı. Değil mi? Then if there is such f bar, then of course f1 x bar is just f x bar is just f bar x1, but this is just f bar px1. Px1 is just y, but of course px1 is also px2, and this is just f of x2. Okay, so f of x1 is equal to f of x2. This way we say this is the following: f is constant on each fiber. What we mean by the fiber is this: you have a point here, you have a point. The pre-image of this point is a fiber of this map. Okay, and f should be constant on that fiber for such an f bar exist. And clearly, if şuraya yazayım onu da, moreover if f is constant on each P inverse of Y on fiber, then of course F bar from Y to Z can be defined as, değil mi? Böyle bir map yazabilirim. Nasıl? F barın görüntüsünü nasıl belirleyeceğim? F barın görüntüsü herhangi bir noktada şöyle tarif edilebilir. F barın y'deki görüntüsü nedir? F'in bir x noktasındaki görüntüsü. X nedir? O noktanın üzerinde rastgele bir nokta. Hangi noktayı seçtiğimin de önemi yok. Çünkü x1'i de seçseniz, x2'yi de seçseniz aynı değeri alıyor. Dolayısıyla bunu şöyle tarif edebiliriz. F of x diye. For any x in P inverse of y. Tamam mı? Okay. Tamam. Yok, bu kötü. Şu iyi. Tamam. Okay. Dolayısıyla so such f bar exists if and only if this f is constant on the fibers of P. What about the second part of the statement? That is neredeydi o? Moreover, in this case, f bar is continuous if and only if f is continuous. But that is also trivial, right? Okay, let me switch the board. Now suppose f bar exists, then if f x to z is continuous, then for any u in z, we have. Şimdi f barın continuous olduğunu söyleyeceğim. F bar inverse of u'ya bakacağız. F bar inverse of u nedir? F bar inverse of u ne bilmiyorum ama aslında şu. Bunun bir de P altında inverse'ünü alırsam, değil mi? F barla bu. Bu ne demek? Bu F bar kompozisyon P inverse of u demek. Değil mi? Inverse'ünü aldığınız zaman yer değiştiriyor. Ama bu neye eşit? Bu F inverse of u'ya eşit. F'i continuous kabul ettik. So if f is continuous, then this is an open set. So that P inverse of F bar inverse of U is open. But if this is open, then this is open because it is open by the definition of quotient topology, right? We say a set in Y is open if and only if its inverse image under P is open. So, so that this is open. Hence, by the definition of quotient topology, topology. F bar inverse U is open. Hence, F bar is continuous. So what we see is this. If this is continuous, then F bar is continuous. We have to also prove the other way around. If this is continuous, then F is continuous, but that's clear. Conversely, if F bar from Y to Z is continuous, then clearly F, what is F? F is just F bar composition P. Now P is continuous, F bar is continuous, therefore F is continuous. Okay. So what is nice about this proposition, you know, is the following. So you have X here and Y here. Usually this Y will be just an identification space. What we mean by that, you have some X and you identify some points. In other words, onto map gives you an equivalence relation, and then you regard each equivalence class as a point. In other words, you just identify points in an equivalence class to a single point. That's why we call it an identification space. And then we have a map, let's say here, and we have another map. Usually it is difficult to describe this object because it's an, you know, it's a set of equivalence classes and so on. And it may be difficult to check that this map is continuous. But this proposition gives us a very, you know, easy way of checking continuity of this map. What is that? This map is continuous if and only if this map is continuous. Okay. So if this is continuous, then this is automatically continuous. That's why this is a very useful proposition. Let me give you a quick example. We will consider this later, but in more detail, but let me just do it for the sake of giving an example. Consider S2, which is just the set of X, Y, Z in R3 such that X square, Y square, Z square equals 1. Okay. As a subspace of R3. S2 as a subspace of R3, it's a closed and bounded set. Why is that? Because it is closed because it's given by an equation. Okay, actually, it is just inverse image of 1 under the map. Which map? Which sends x, y, z to x square plus y square plus z square. Right? If you consider this continuous map, then S2 is just the inverse image of the point 1 under this map. Therefore, since point is closed, its inverse image is closed set. and it is bounded because it is contained in a ball. Therefore, it's a compact space. It's a compact Hausdorff space. You may also regard it as a metric space. Okay, it's a metric space because it's a subspace of R3. It's a and it is compact. We define the following gadget: real projective space or real projective plane. Real projective plane. This is the space on which you make projective geometry. Okay, projective geometry. It is basically real. It is basically the plane R2, but you have an additional line called the line at infinity. Have you ever taken or exposed to projective geometry? No? Okay, I'll talk about this later, but for the time being, so this is basically the whole plane, Euclidean geometry, but you have an additional line at infinity called the line at infinity. In this geometry, any two lines intersect. There are no parallel lines. Any two lines intersect and so on. This is defined as follows. RP2 is defined in two different ways. First, you may just consider all R3 except the 0. And then you do the following. You just consider lines passing through the origin, and you consider each line as a single point. So what you do, you just identify X, Y, Z with lambda times X, Y, Z. Okay, lambda is any real number. Any real number. So what is this? You see, whenever you have a point in R3, you identify this point with any other point on the line containing this point. So if this point is X, Y, Z, let's say this is just lambda times X, Y, Z. So you just take this line that passes through the origin and consider it as a single point. That point is a point in your projective plane. Okay. Burada aslında bu niye R2'nin işte extension'ıdır diye düşünürseniz şöyle düşünebilirsiniz. Şimdi R2 bizim bildiğimiz düzlem şu, değil mi? Burada herhangi bir nokta aldığınızda düzlemde şunu yapıyorsunuz. Bu noktayı 0, 0 bir noktasıyla birleştiriyorsunuz. Yok, pardon, birleştirmiyorsunuz. Ne yapıyorduk? Bir dakika, düzlemdeki her noktayı doğruya, yok böyle değildi. Karıştırdım. Bir dakika. Herhangi bir nokta aldığımızda onu R3'te şimdi x, y 0 bunu 0, 0 1 ile birleştiriyorduk sanki. Bir dakika. Karıştırdım orayı ya. Neyse. Onu sonra anlatayım. Şimdi karıştırdım şeyi. Neyse şöyle devam edeyim. Şimdi RP2'yu böyle görebiliriz. I'll describe later how we see this as real projective plane. But the observation is the following. You see, here each line through the origin is considered as a single point. But I can regard this also as follows. Consider the unit sphere here. Unit sphere here. Unit sphere intersects each line passing through the origin in 2 points, right? Let's say this point and then this point, right? One point where it intersects the sphere and goes inside the sphere, and the other point where it just leaves the sphere. And since I regard this line as a single point in RP2, I can do the following. Instead of considering lines, I may consider the intersection of each line with the sphere, and I obtain 2 points, conjugate points. If this point, let's say A, B, C, then of course this point is minus A, minus B, minus C, right? It is just the antipodal point, right? Every line through the origin intersects the sphere in 2 points. And these points are antipodal in the sense that one of them is just minus 1 times the other point. Therefore, I may regard RP2 as the sphere divided by the following relation. This point is identified with this point. So you just take the sphere and identify each point with its antipodal, glue them, and what you get is your projective plane, okay? So we have then the following quotient map from S2 into RP2, where this is just obtained by this identification, okay? And what is nice about this, since this is a compact Hausdorff space, this is an onto map and continuous map. Therefore, this is also compact, and it is still Hausdorff. Hausdorffness doesn't come from the fact that this is Hausdorff. In general, quotient of a Hausdorff space can be something really terrible. It doesn't have to be Hausdorff, but this gadget is still Hausdorff. Why it is Hausdorff? Well, it is because of the following. If you have 2 distinct points on RP2, so if you have 2 distinct points on RP2, it means we have 2 different lines. So one line is this and another line is this, okay? I can just choose an open set like this and open set like this. And then of course this open set has a mirror image here and this one has a mirror image here. But you can choose these open sets so small that they do not intersect. And in the quotient, these two open sets glues to each other and gives me, suppose this is our RP2. So these two open sets gives me an open set like this, and these two open sets give me an open set like this. Therefore, still for any 2 points on the RP2, I can choose disjoint open sets containing those points. Therefore, this is still Hausdorff. And it is actually a useful fact that this is a Hausdorff space. Why is that? You may consider the following map from S2 into R5. Let's say this is F, X, Y, Z is this. X squared, Y squared, Z squared. Z square gerek yok. XY, YZ, and XZ, okay? And then here I have RP2, which is S2 divided by this relation. And then you see this map, what are the fibers of a point here? Now, if I have a point ABC here, its image in the projective plane, the image of this point is denoted like this. Homogeneous coordinates, we say this is the homogeneous coordinates. And above this point, we have actually 2 points. One of them is this, and the other one is minus ABC. Okay? And both of them lies above this. And note that F is constant on these 2 points, right? F of ABC is the same as F of minus A minus B minus C, right? F is constant. Therefore, I have a map here so that this diagram is commutative. In other words, F is just F bar composition P. And clearly, this is a continuous map, right? F is continuous. Because it's a polynomial map from R3 into R5, and it is the restriction of this polynomial map to the unit sphere. It is continuous, and therefore, so this implies F bar is continuous. And moreover, we have the following. This F is not one-to-one, of course, because F of ABC is F of minus A minus B minus C. It is a 2-to-1 map. This is a 2-to-1 map. But F bar, you can check that it is 1-to-1. F bar is 1-to-1. And then we have what? F bar is a continuous 1-to-1 map. And this gadget is a compact space, and it is Hausdorff. Therefore, by the homeomorphism theorem, you proved the homeomorphism theorem in 349, I guess, and also if you have taken any topology course, you have seen there. This F bar becomes an embedding. Okay, so since F bar from RP2 into R5 is 1-to-1 and continuous, where Y is a compact Hausdorff space. Hausdorff space. F bar R5 is an embedding. Embedding means it is homomorphic onto its image, okay? Therefore, R5 contains a copy of RP2. Actually, you can modify this map. You can modify this map and obtain an embedding into R5. So it is possible to modify this map and obtain another embedding, let's say, into R4, okay? That's possible. You just, I don't remember now, but instead of this, you write something like this. XY, YZ, and then, I don't know, plus X square or something like this. Ya da yani şöyle bir şey yapınca oluyor da şimdi hatırlamıyorum. So it's possible to embed RP2 into R5, R4. However, it's a fact that RP2 does not embed into R3. Yani RP2'yu R3'in içine koyamazsınız. Tamam mı? O mümkün değil. İspatı da intersection teori kullanıyor. Intersection teori kullanmazsanız daha fazla algebrik topoloji kullanmanız gerekiyor. Çok trivial bir şey değil aslında o. Yani RP2'nun R3 içinde yatacak yeri yok. Öyle diyebilirsiniz. R4'e ancak gömülebilir. Gerçi gene bu şanslı. Öyle manifoldlar var ki, kompleks manifoldlar hiçbir kompleks space'in içine girmiyor. Yani real case'de her manifold bir array'nin içine girer. Onu da ispat eden, ya o basit bir şey de. Hatta şey neydi o? John Nash şey de söylüyor. Manifoldun üzerinde bir Riemann metriği varsa, yani bir yerde uzunlukları ölçebiliyorsanız, öyle gömerim ki diyor arene, uzunlukları da koruyacak şekilde izometrik embedding bulabilirim diyor. O John Nash'in teoremi. Yani her reel manifold bir arenin içine giriyor o anlamda, ama kompleks olunca kompleks yapısıyla beraber gömebilir misiniz bir manifoldu? Kompleks affine uzaya CN'e. O sorunun cevabı olumsuz. Ve işte örnekler var. O manifoldlar, kompleks manifoldlar, kompleks yapısıyla beraber hiçbir CN'in içine girmiyor. Yani kompleks manifold olduğunu inkar ederse girer, ama ben kompleks manifoldum diyorsa hiçbir kompleks manifoldun içine giremiyor. Bu RP2'nun R3'in içine girmemesinin ispatı oldukça hoş bir şey o. Benim sayfamda bir tane video var, onu anlattım. Ona bakabilirsiniz. Okay. Şimdi quotient space bu. Şeyi söyleyeyim aslında. Bu RP2'yu şöyle diyeyim. Şimdi RP2'yu şöyle görüyoruz ya, RP2'yu S2 divided by ABC minus A minus B minus C diye görebiliriz. Burada şöyle bir şey yapalım. Şimdi küreyi düşünelim. So I would like to draw a picture of RP2, okay? This is what we can do. Take this two circles, seçebilirsiniz, dönenceler. Şimdi şurada bir tane, değil mi, böyle bir şey var, küre parçası var. I have another piece of sphere, and under this action, this piece is identified with this one. So let me consider this identification space as follows. First, let me cut the sphere from this circle and this circle and obtain three pieces. This part plus this part and then the middle part. Now, this part and this part are identified, right? Any point here is identified with this point. So these parts, let me call it D1 and D2, they are identified and they will give me, so when I divide this into this, so D1 and D2 will be identified and will give me a disk. So this is D1 and D2 identified. Değil mi? Bu parça bununla identify ediliyor. Yani identify'dan kastettiğim şey şu. Buradaki her bir noktayı görüntüsüne yapıştırın. O da ne demek? Alıyorsunuz bu takkeyi öbürüne yapıştırıyorsunuz. Başka bir şey değil. Peki ortadaki kısım ne oldu? Ortadaki kısım hala duruyor. O şu. Değil mi? Şöyle silindir gibi görebilirim onu. Silindir gibi görebilirim. Burası hala identify edilecek, değil mi? Yani şöyle. Özür dilerim. Okay. Orada da şöyle bir identification yapayım. Şimdi burada nedir? Şu orijin şurada. Orijin. Şurada bir mesela nokta aldığınızda, değil mi? Bunu orijine birleştiriyorsunuz. O doğru bu küre parçasını bir nokta daha kesiyor. Aynı şekilde mesela şurada bir nokta alırsanız işte şurada bir yerde kesiyor. Bu noktaları eşleyeceğim. Oradaki eşleme işini de şöyle yapalım. Bu silindiri, let me take this cylinder and cut into two pieces like using a plane like this. So I have two pieces like, so one piece, so this is just one piece like this. Okay, and then another piece like this. Yani bir belki şunu şöyle mi çizmek lazım? Yani şu silindirdi ya şöyle. So this was a cylinder like this. I cut into two pieces. One piece is like this, another piece is like this, okay? So they are glued like this and form a cylinder. One is back part, the other one is front part. So to consider the picture of RP2, what I do, I cut this into smaller pieces and then make identifications on those smaller pieces because it is easier to visualize. And then I have to glue back these pieces, right? Now, these two parts were easy because I have one copy here, one copy here, and then they are just identified, and that will give me just one copy of disk. And here I cut it like this. So I cut through this line and let's say this line. Let me just indicate them like this. So it is this one, and then I have this one. I know that this thing will be glued back to this, and this thing will be glued back to this one. Okay? Then we do what? We identify this piece with this piece, right? Because this any point on this front part is identified with a point on the back part. Therefore, this will be just identified with this one. Therefore, I can just erase one of them. So we have only one copy, right? Because once you identify, this is gone. But you have to be careful. Why is that? You see, still, I have to make some identifications. What are they? I identified every point here with a point here, but the points on this two line segments are not identified yet, and they need to be identified because any point here is equivalent to this point. Therefore, this line segment here should be identified with this one. So what you have to do, you have to identify this line segment with this one, but in the opposite directions. What we mean, you see, this point is identified with this one, and this point is identified with this one. Therefore, as you go like this, actually you are going in this direction. So what you have to do then, I have this gadget, which is just, let me just draw it like this. And so this is a piece of, again, you may consider it as a rectangular piece. And what you have to do, you have to identify this edge with this edge. And if you do that, if you identify this edge with this edge, what you get, take a strip like this and identify this edge with this edge, but in the direction where using these arrows, okay? What you get is a Möbius band. So this will give me a Möbius band. Okay, a Möbius band. Now, so as a result of these identifications, I have one piece of disk and one piece of Möbius band. And remember, these were glued to each other. Now what will happen? The two boundaries here became one boundary, which is this one. And what about the other boundary, boundary of this gadget? It was these two circles, but then they are identified and they give me one circle, right? Here we had two circles as the boundary. Those boundaries were also boundaries of these two disks. They were identified and gave me one circle. And here also, after this identification, this circle is identified with this one, and it is the boundary of this Möbius band. So this Möbius band has boundary which is a circle. So this is a circle, right? It is just one circle. And this is also a circle. And what we do, we just identify this circle with this circle. In other words, you take this Möbius band and this disk and glue them along their common boundary. Tamam mı? Tabii bunu evde yapamazsınız. Hani bu diski alın, bunu da alın. Bunları yapabilirsiniz. Hani kumaştan yaptığınızı düşün. Ama bu boundary'yi buraya yapıştıramazsınız. Çünkü bu iş R3'te yapılamaz. R4'e çıkmanız lazım. Tamam mı? So RP2, that's why can be seen as follows. This is just a copy of disk and then a copy of Möbius band. So Möbius band, and you identify them along their common boundary. So this operation means that you just glue them along their boundary, okay? Using a homeomorphism. This circle is this is a circle. Boundary of this one is another circle. You just glue these two disks, okay? İyi, zaman biraz da geçirmişim. Let me stop here. Kaydı durdur.